Hey everyone, my name is Josh. I'm a third year materials engineering student at the University of McMaster. And if you're watching this video, you're probably in a very similar situation as me, and you're starting to take a class called heat transfer. Now, at the beginning of this class, this seems very confusing, yeah, at least to me. And there's a lot of expected knowledge for us to use in different circumstances and different problems. You might be struggling with it, as you know, I was as well. I'm coming to you here today to give you the kind of the basics of heat transfer, what my class has learned within the past 2 weeks. So without any further ado, let's get started. We're going to be hopefully getting through the first 2 weeks of lecture in this review video. So first and foremost, before we can get into anything, why does heat exchange occur? Heat transfer. Why does it happen? Well, it's due to something we all know called a driving force. Now, what do you think this driving force might be in heat transfer and heat exchange? What's a force, some energetic value that's causing heat to be exchanged or transferred? This is in the form of change in temperature or a change in your phase, which we'll get to a little bit later. Now, how is heat transferred? More specifically, what I'm trying to ask is, in what direction is heat transferred? This is very important as it's going to allow us to understand a lot of assumptions that we're going to have to make in future problems. How is heat transferred? It goes from the hot side to the cold side. Now, this might seem simple in theory, but it's a very powerful assumption that we're going to have to make in a lot of problems going forward. Here's a few of the main variables that we're going to be using. We're going to come up over and over again. Thermal energy, yeah, it's important, but we haven't used it a lot yet. Temperature, obviously very important. Remembering temperature is a scalar, it's not a vector, it has no direction, just magnitude. Heat transfer, that's just a general term. Heat transfer is thermal energy transport due to temperature gradient, which is a change in temperature from side A to side B, which we just said, going from hot to cold. Heat is the amount of thermal energy transferred. That would be big Q. Most of the time, we're going to be concerned with the heat rate, which is the thermal energy transferred per second. And this is a little q. From here, two other variables that we're going to be kind of interested in is heat flux. Heat flux is just the thermal energy transferred per second per surface area. So I don't know, if I lit a flame next to my hand, how much heat is being transferred through my two-dimensional surface area of my hand. And that's Q double prime. And remembering these units, little q is in joules per second or watts, and then Q double prime is in watts per meter squared. The final variable that we're going to be dealing with a lot is volumetric heat flux. Basically the same thing as regular flux, except instead of doing the heat through a two-dimensional surface, we're doing heat through an entire three-dimensional surface, like a box. And that is notified by Q dots. And it's in watts per meter cubed. All right, easy enough. Now, we just talked that the driving force for heat transfer is due to two different things. It can be due to a change in temperature or a change in phase. Now, I want to introduce you to the two different types of heat transfer: sensible transfer and latent transfer. What do you think keyword sensible transfer is due to? Well, what kind of driving force? Sensible transfer is due to a change in temperature. Whenever there's a sensible heat exchange or a sensible heat transfer, this is due to a change in temperature in your system. Keyword sense, because this is something that you can sense, something you can feel. I can feel a change in temperature I can put my hand against these two walls and feel, hey, this wall is hotter than this one. Sensible. So we'll just say a change in temperature is the driving force. Now, what is latent heat transfer? Now, if you go back to our two different driving forces, it's obviously the second one. It's due to a change in phase. What is latent heat transfer? Well, it's the energy that the molecules have to overcome in order to phase change. When you have a solid, right, ice, these molecules are tightly packed together. When they are in the presence of heat, they start pulling away from each other. The energy needed for these molecules to pull away from each other and become liquid molecules is the energy of latent heat transfer. Energy to overcome molecular force. This is change in phase. Driving force. E. Cool. So the two different types of heat transfer, conduction versus convection. You've probably heard of both of these. Well, let's talk about that. What is conduction? It's going to be the transfer of heat from A to B due to random motion. Contact. So always think conduction, contact. Heat transfer due to random motion. Contact. Now what's convection? Well, this is heat transfer due to random motion. And bulk. What's the difference between conduction and convection? Conduction is due to contact in solids. Convection is due to molecular contact in fluids, liquids, or gas. So let's say, for instance, I have some ice cream. I put it outside. Ice cream starts to melt. That's convection. I put my hand on the stove. My hand gets hot. That's conduction because I'm actually physically touching something. Now, here are some different important formulas that we're going to have to use for convection and conduction. So, heat flux due to conduction, this equation here, where K is the thermal conductivity, and the heat flux due to convection is this yellow equation, and H is just another constant that we're going to use instead of thermal conductivity. This essentially is its equivalent in convection. We're not going to really talk about radiation. We don't talk about that in this class, but just know it's a type of heat transfer that can happen. Cool. So we use some thermodynamics in this course, not a whole lot. All you need to know is the first law of thermodynamics. The change in total energy in a system is equal to the change in the internal energy plus the change in kinetic plus the change in potential. This equation is also equal to heat minus work. We don't touch on that one too much. What is very important, though, is this term here. Accumulation is input minus output plus generation minus consumption. So in a system, the accumulation of anything, and this can be energy, this can be heat, this can be heat rate, this can be Gibbs free energy, entropy, anything. the accumulation is equal to, in this case, we'll say heat or heat rate, the heat rate in minus the heat rate out, plus the heat rate generated within the system minus the heat rate consumed inside the system. Cool. Hopefully you follow. Take that in. We're going to be moving on to a very important derivation. So if you need to take a break, come back, important derivation coming right up. You can't miss this. Ready? I'm going to start with the plates. This plate has some kind of thickness, T. Let's say the thickness is equal to L. L meters long. The left side, our X variable is equal to 0 because we're at the starting point. X is equal to 0. At the end point, my X is going to be equal to L. So I start at X is equal to 0, and I'm going to travel until X is equal to L. The left side of my sheets has T1. The right side of my sheet has T2. But right now, let's just say they're two different temperatures. Now, I want to find out how I can measure the heat exchange in this sheet. First, I'm going to start by asking myself, well, how can I measure the change in energy as a function of time? So over time, how does energy change? Well, we know accumulation, which is just d over dt for energy, is equal to energy in minus the energy out plus the energy generated. And we're going to assume no energy is consumed. Now, something that I can do is I can change E to be dq. All that I have to do is I have to recognize that there's no work being done in this system, and I can say, hey, E is equal to Q. So now we have dq over dt. And if you don't know how I got to E is equal to Q, well, let's look up here. So energy is equal to Q minus W. My system is going to do no work. W is then canceled out. E is equal to Q. Cool. Now we have dq by dt. This is the change in heat over the change in time. What's this equal to? This is a rate. This is the heat rate. What variable are we going to use on the right-hand side? Let's use little q, our heat rate variable. This is equal to q in minus q out plus q generated. I can further manipulate q. I know that q is equal to m c p delta t, where Cp is the specific heat capacity. I also know that mass is equal to volume times density. And I know that volume is equal to cross-sectional area multiplied by thickness. In this case, we'll say that's the change in X. So let's substitute in all of these variables. We have Q is equal to mCp delta T. Delta T is the same thing as dt. It's just the change in temperature. So let's bring that step to the outside. Cp. Now we have d over d little t. Now I only wrote Cp down because we manipulated mass. And we said mass is volume times density. And density is going to stay. So let's keep density there. We then manipulated volume and said that's cross-sectional area multiplied by our change in X. What do we know about our change in X? Well, that's the same thing as saying dx, the change in something. AC, we'll keep it as delta X, but just be aware that it's the same thing as saying dx. We did not manipulate our right side. All right. You forget. mass change into this, volume change into that. Cool. Let's keep going. So I can further manipulate the right-hand side by saying Q in minus Q out. That's the same thing as saying minus Q out minus Q in. If you distribute the negative sign, you're going to get what we have in yellow. That's just equal to negative delta Q minus dQ. Hopefully, you're understanding that. Now, from here is where we do some tricky stuff. So I'm going to keep rho Cp d temperature over d time. That's now going to be equal to Q gen minus delta Q. Let's put that in brackets. From here, we have to divide by 1 over delta X times AC. Now, we're gonna distribute AC delta X. Remember, that's just volume. We're gonna distribute that into these brackets. But first, let's manipulate delta Q a little bit. So we have Q gen, but we know delta Q is going to be equal to delta Q is going to be equal to minus K AC dt by dx. Now, why do we know that? Well, let's think about what we were saying earlier. dt by dx times negative K. We saw that equation. That is the conduction flux. We want Q, the heat rate. We know that Q double prime, the flux, is negative K dt dx. This has units watts per meter squared. We want watts. What are we going to do? We're going to multiply by AC. Beautiful. Let's move on. Remember what we said before? What is Q divided by a volume? That's our volumetric heat flux. So now we get Q dot gen. And we can do something really cool. And we can say that 1 over AC times 1 over d delta X is just 1 over AC times d by dx. It's the same thing. Now what we can do is we can multiply this by our negative K AC dt by dx. Now we know we're using a slab. Our cross-sectional area is not going to change. Boom, boom. And in most circumstances that we're going to be learning, or at least right now, K is constant. So we can pull out all the constants and we can multiply our equation by our d by dx. Our final equation, rho Cp, the temperature by d time, is equal to Q gen plus, because we have two negatives being multiplied by each other, K d squared T by dx squared. This is the form of the heat equation that we're going to become very familiar with. Okay, so based off of different cases and different conditions, we're going to have different forms of the heat equation. Now, the one that we just derived is the general form, assuming that assuming that we're in only one direction and we have constant cross-sectional area and constant K. Now, all four cases that we're going to go over now assume steady state. What is steady state? Steady state says d of anything. Well, let's just say this is, I don't know, dB. dB. Change in anything over the change in time is equal to 0. How can we manipulate our equation now? Well, we can just take out the left-hand side and equate it to 0 for all of our equations. Now, in the first case, Q gen is equal to 0. So we can do this. This leaves us with 0 equals k d squared t over dx squared. We can get rid of k by just dividing both sides by k. We integrate twice. Our first integration gives us c1 dt by dx. We're going to integrate again, and we get t as a function of x is equal to c1x plus c2. Have no q gen. This is the equation you're going to end up. Not bad, right? You integrate once, you get c1, integrate twice, c1's multiplied by x, you get c2. Cool. Now we got to worry about some boundary conditions. These are going to give these boundary conditions what's happening at x is equal to 0 and what's happening at x is equal to t2 is going to give us what a constant are. So remember, we have 0 and L. This goes for all of these cases. Now our boundary conditions say that when x is equal to 0, we're going to have t1, and when x is equal to L, we're going to have t2. Now when we plug in 0 to our equation, we're going to find out that c2 is equal to t1. When we put L into our equation, we're going to say that t2 is equal to c1L times t1, which is what we just found c2 to be. We use some algebra. We find that c1 is going to be equal to t2 minus t1 all over L. So finally, we get t of x, t2 minus t1, L plus t1. So I give you the boundary conditions. I went through how we're going to simplify our equation. I showed you what the final answer is going to be for C2, C1. If you're not convinced yet, I ask you to do the math. Because, you know, this course, I'm just going over the science and stuff behind all this stuff. Hopefully the math isn't too crazy. All right, case 2. Q gen is not equal to 0. Oh my goodness, what's going to happen here? So we grab this equation. We know we have steady states. Like I said, steady state is assumed. Boom. But we have Q gen. So we're going to get negative Q gen is equal to K. Now let's just do negative Q gen over K. Is equal to d squared t over dx squared. Integrate once. We're going to get negative Q dot gen over K. We got to multiply by x because we just integrated. What's some constant? dt by dx If we integrate again, t as a function of x is equal to, let's integrate negative q gen over k times x. Let's think. Q gen is going to be the same. We're still going to have k. Our x is still going to be there. But what's the integral of x? It's x squared over 2. Then we're going to add an x to c1 because we just integrated it. And we have another constant, c2. This is the general format if you have QGen in your system. This is the general format. Now let's talk boundary conditions. Well, we're given T1 and we're given T2. Our T at 0 is equal to T1. Our T at L is equal to T2. We do some algebra and we find out that T of X is going to be equal to negative Q gen over 2K times X squared plus, we're going to have something times X plus, this is the easy one, T at 0 is equal to T1. When we plug in 0, everything goes away except for C2. So C2 is T1. When we plug in L, our stuff stays. So we kind of have to do some algebra. We end up getting T2 minus T1 over L plus Q gen L over 2K. That is equal to C1. Bada boom. And again, if you're not convinced, I invite you to do the algebra yourself. Feel free to ask me some questions. All right, next condition, adiabatic with Qgen. So we can start. We know we have Qgen, so we know we're going to have this general equation. Now, what are our boundary conditions? We know we have an adiabatic surface. This means that Q cannot leave our system. Heat cannot leave. So what's our heat rate? Maybe not heat rate. What's our flux? Our flux, since I'm going to have no Q, no heat leaving my system, nothing's coming out. My flux of the back wall, my flux at L is going to be equal to 0. This means negative K dt by dx is also equal to 0. In simpler terms, we can say one of our boundary conditions is that dt by dx at L is equal to 0. We're given T1, that's great. That means at T is equal to 0, we have T1. Nice. Now, we know, obviously, now that C2 is equal to T1. But how are we going to get the second boundary condition? First, we're told that dt by dx at L is equal to 0. So the first thing we have to do is we have to find dt by dx. How do we do that? We just take derivatives. So the derivative of negative q dot gen over 2kx squared is just q dot gen over k, negative q dot gen over k times x. The derivative of c1x is just c1. Now, we're going to plug in we're going to plug in L. We get 2q dot gen over k times L plus C1 is equal to 0. So C1 is just q dot gen over k times L. Finally, for this equation, T of X is equal to negative q dot gen over 2k times x squared plus q dot gen over k times L times x plus T1. Cool. That's not awful, right? I personally don't think it's that bad, but you guys can be the judge of that. Now, case 4 is a constant flux, or delta Q flux. The change in our flux is equal to 0. What this just means is we're given the flux at some points, and we know it's equal to a certain value. So where we have Q gen, our setup's the same as Q3. Our boundary condition, we're given T1. We're given the temperature at 0. Temperature at 0 is T1. Now, we know our flux. We know what it is. That's equal to negative K dt dx. So dt dx is equal to our flux divided by negative K. That's our second boundary condition. So in this situation, our flux at L is equal to Q double prime over negative K. From there, we can rearrange and solve. In this situation, I'm just going to show you what T of x is equal to. It's kind of messy. If you can do the math, try it out, you're going to end up getting this expression. Just like that. Sorry, I just made a slight typo. This is going to be your units. And excuse me, this is your reasoning here. Okay, let's do a practice question. I think practice questions always help. And this is just a bit of notes. Just noting that negative K dx can be a boundary condition. All right, so let's read this practice question. The steady state temperature distribution in a one-dimensional wall of thermal conductivity 50 watts per meter Kelvin and thickness L is equal to 50 millimeters is observed to be Tx equals a quadratic function. At x is equal to 50 millimeters, the wall has an observed temperature of 100 degrees C and experiences convection with the fluid at T infinity equals 25 degrees C with a convection coefficient of H is equal to watts, 15 watts per meter Kelvin. Find A and B as long as Q gen. All right, and let's write our notes. K is equal to 50, H 15. We have a thickness of 50 millimeters, 0.005 centimeters. We're given T2 or TL is equal to 100 degrees C, which is equal to 373 Kelvin. T infinity, that's just kind of whooshing around here. Let's say it's like air or something, I don't know. And convection, 5 degrees C, which is equal to 298 Kelvin. We know T of x is in the form a plus b x squared. Now, we only require two boundary conditions, but there's actually three. So let's just do the ones that we need first, and then I'll show you the third one. We know that the first boundary condition is we have the temperature at L that's equal to 373 Kelvin. Easy peasy, beautiful. We also know that dt by dx at L is going to be equal to the convection, the flux from convection, divided by negative K. Divided by negative K. And we want the flux to be a positive number. If the flux is a positive number, this means that the direction that we're defining as positive is the way the flux is going. So let's put it this way. I think that the right, anything going to the right is our positive. This is positive. Meaning I think T1 is going to be greater than T2 because our heat is going to be transferring from left to right. I also know that T infinity is the outside layer of my brick or my wall, let's say. And the temperature here at T infinity is cooler than my temperature here, where T2 is 100 degrees C. So I'm going to say the change in temperature is T infinity minus T2. That'll give me a negative number. I'll divide it by a negative number, giving me a positive. Cool? Cool. Okay, third boundary conditions. You don't need it. Good to know, though. So let's take a look at our equation. We have a quadratic. This quadratic is bx squared plus a. That's odd. We know we have qgen because it's a quadratic, but we only have C2, so which is a, and we don't have anything multiplied by x. What does that mean? Well, let's think boundary conditions. How can we get a boundary condition that has both a, which is our coefficient without an x, and and we don't have our other one, that's our coefficient with x? Well, if we take dt by dx at 0 to be equal to 0, this is exactly what we get. We take the derivative of this will go away, this would go away, this would be x, this would go to 0, bada boom, C1 is 0. That's just a little, just a little something to know. It's not super important for this question, but it's nice to know. So we have our boundary conditions. Let's plug it in. So we know a couple different things. Right away, we can take the derivative of our thing box in blue. dt by dx is equal to 2b times x. Now we know at L, we have h T infinity minus T2 divided by negative K to 2BL. L is 0.05 meters, T infinity. We can just say that's 25 because we're subtracting T2, which is 100. We don't have them all to convert it into kelvins. We know H is 15. We know K is 50. plug it all in. We're going to get B is equal to 225. So now we have d of x is equal to a plus 225x squared. We know that T is equal to 0.05 meters. Our temperature is equal to 373. We rearrange and solve for A. A is going to be equal to 372.44 Kelvin. So our equation, 372.44 plus 225x squared. Nice. Okay. This question then asks us to find Q gen. There are two different ways to find Q gen. There's a way that requires you to go out of your way and do something else. We can do that, which I'll show you what it is, but it's very simple, okay? Rather than doing an energy balance equation, we're given the form of our answer, a b squared times x. Now, we know our coefficient in front of x squared from this equation here, which we derived. We know that b is the coefficient in front of x squared. The coefficient in front of x squared is always going to be equal to, when q gen is present, negative q gen over 2k. We know what b is, we know what 2k is, we rearrange, and we get q gen is equal to negative 22,500. How easy was that? We didn't even have to do an energy balance equation. We didn't even really have to think. Now we can do that, or we'll do an energy balance just for laughs. So we know our accumulation is going to be 0. We know that's equal to Q in minus Q outs plus Q gen. You know what? We'll just say the heat rate out. Whatever. Now we know Q in is going to be equal to 0. We just said that in our boundary conditions. No heat rate. So Q out is equal to Q gen. Now we know Q out is going to be equal to the flux times the cross-sectional area. And we know that Q gen is going to be equal to the flux times the cross-sectional area. So let's start with Q out. We know what the flux for Q out is. It's convection. Q out is convection. We know this. We've been told this in the question. And we have to multiply this by the cross-sectional area to go from flux to heat rate. Now, we want to find Q dot gen, which is the volumetric flux. We do this by taking Q gen, our heat rate generated, multiply it by our cross-sectional area. We take Q dot gen. Q dot gen is what we want. We need it in the equation. Take Q dot gen, which is watts divided by meters cubed. We multiply it by our cross-sectional area. We then have to multiply it by our thickness or our length in order to cancel out the meters cubed. Dimensional analysis. Boom, boom, boom. Not on both sides. We can then cancel out cross-sectional area. Gen H T infinity minus Ts divided by L. That is also equal to negative 22,500. Which way is easier? I think my way is easier. I think it's much easier just to recognize that, hey, this coefficient is equal to something that we just derived. You don't have to go and do all this other fancy stuff. You can just keep it nice and simple. To each their own, I guess. Okay, let's talk about the last piece of content that we're going to be going over. Thermal resistance. So we know that from any circuits course, resistance is going to be equal to a driving force divided by a rate. This is derived from V equals IR, where R is the resistance, V volts is our driving force, and I is the rate of our current. Rearrange, just like that. So we have a driving force in heat transfer. We just mentioned them. It's either going to be a change in phase or a change in temperature. In this case, sensible change in temperature. So there is something called heat resistance. It's how walls resist heat exchange. That's going to be equal to our driving force, which is a change in temperature, divided by a rate. What rate have we been working with? The heat rate, Q. Now, our total resistance can be found using this. This is our resistance for our entire system that we're looking at. Now, individually, resistance is calculated different ways based on conduction or convection. For conduction, resistance is equal to the thickness of whatever you're analyzing divided by K as a cross-sectional area. For convection, it's just equal to 1 divided by H times the cross-section. Nice and simple. Nothing too hard. That's all the theory, really. Let's hop into a practice question. So what's nice is we can draw out all of our systems just like a circuit. So for this question, it says the heat transfer rate through a wall is 500 watts. What should the thickness of the insulation layer to keep the room at the temperature 20 degrees C? The brick thickness is 5 centimeters at each side. Convection coefficient outside is 5, inside is 10. Yeah, the other way around. Inside is 5, outside is 10. Temperature outside is -5. Cross-sectional area is 25 meters squared. K values are constant. So how are we going to do this? Let's find out the resistance in each slice, in the brick, in the insulation, and in the other brick. So our brick is going to be the same for both, because we have the same thickness of brick, K is consistent, all that stuff's cool. So the thickness, L, is 0.05 meters, divided by K is the same, 0.72. The cross-sectional area is the same, 25. This is going to be 2.778 times 10 to the -3. The resistance of the insulation, we don't know how thick it is. So it's going to be L divided by 0.14 times 25 meters squared. Now we got to factor in the convection outside and inside, because this is also going to change the resistance. It's going to change the heat and also change the temperature. So our convection will start outside. That's equal to 1 over H times the cross-sectional area. H outside is 10. That is equal to 4 times 10 to the -3. Our convection inside is equal to 1 divided by 5 times 25. That's equal to 8 times 10 to the -3. What we're going to do now is our total is going to be equal to the change in temperature divided by Q. The change in temperature is going to be T2, T infinity 2, 20 degrees C, minus T infinity 1, negative 5 degrees C, divided by the heat, which is 500 watts. That's going to be equal to some value, 0.05 Kelvin per watt. We then are going to take the sum of our resistances. Why the sum? Well, this is showing that all of our resistances are going to be in series. We're going to start with the resistance from the convection. Then we get the resistance from the brick. Then we get some more resistance from our insulation. We get some more resistance from the brick. We finalize with some more resistance from convection. We finally get our T infinity. So we're going to add all of these up, but wait, our goal is to find L. So what we're going to do is we're going to keep resistance of our insulation on one side. We're going to take the rest of the sum, we're going to bring it over, we're going to do 0.05 minus the sum of our resistance. That doesn't include the insulation, which will give us L is equal to 0.1136 meters, or 11.36 centimeters. It's not too hard. Hopefully you guys could keep track. But I don't think it was all that difficult. Okay, this is our last practice problem of the video. We get this, you guys can get out of here. So, an electronic component is composed of 3 different materials shown in the figure below. The left side component is exposed to a constant heat flux of 500 watts per meter squared, while the right side is exposed to a cooling fan, which maintains a convective environment at 25 degrees C and 10 watts per meter squared degrees. Determine the temperature of the left wall component. All right. We know what T2 is. We don't know what T1 is. Let's think. RT, the total resistance, is equal to delta T divided by Q. Okay. So we know that delta T is equal to RT times Q. But what is delta T? This is where you got to pay attention to detail. We know that heat flows from hot to cold. We are told that the heat flux is positive and goes from side 1, where T1 is, to side 2. Therefore, what's going to be hot? T1 or T2? We flow from left to right, hot to cold. This shows that T1 is hotter than T2. If delta T was T2 minus T1, what will that happen? I'm going to get a negative number. We don't want negative resistance. We want positive resistance. So what we're going to do is delta T is going to be equal to T1 minus T2. This is going to be equal to RTQ. T1 is going to be equal to RT times Q plus T2. We have everything except for RT. Let's find RT. Well, this one's a little bit tricky. Let's draw out our circuit again. So we have, I'm going to draw it in red this time. We have some convection. We have resistance from A. We have resistance from A again. We got some more convection. Or, sorry, rather, we don't have any convection at the beginning. That's my mistake. No convection at the beginning. We weren't told. But we do have convection at the end. From here, we're going to have resistance due to C. We're going to have some resistance due to B. And we're going to have more resistance due to B. What kind of circuit does this look like? If you said parallel, you'd be correct. So we're also going to need the cross-sectional areas of each slice, because that's given in our conduction equation. Remembering these rules. We can find easily RA is going to be equal to how thick is A? 0.2. We're going to divide that by 100, which is K, multiplied by its cross-sectional area, which I found up here. 8 times 10 to the negative 4. Each RA is 0.25. RB, you get thickness of RB is 0.05 right here. Divide that by 5, multiply by the cross-sectional area, times 10 to the negative 4. We're going to end up getting 50. RC, that's 50 for each of them. RC is going to be equal to 0.05 divided by 10, which is that K, times 4 times 10 to the negative 4. That's going to be equal to 12.5. Cool. From here, RT is going to be equal to what's in series? What's in series? First off, what is in series? Well, RA is in series with our parallel component, which is in series with RA, which is then in series with our convection. So we have 2 times RA, which is 0.5, plus the resistance of our parallel component, plus our convection, and that's 1 over H, which we were given as 10, multiplied by the cross-sectional area. And that's the same thing as A, just 8 times 10 to the negative 4. Now, what do we know about parallel circuits? Well, they use a different rule. You got 1 divided by each resistance. Then you got to inverse that. So RP is going to be able to even out to 1 divided by 50 plus 1 divided by 50 plus 1 divided by 12.5 inverted, which is equal to 8.33. Therefore, our total resistance is going to be equal to 133.833 Kelvin per volts. We then swing back to our original equation. T1 is going to be equal to 133.833 times Q plus T2. We can keep it in degrees. That's 100 degrees. What is Q? I'll tell you what it's not. It's not 500. Why? Because we were given the flux. The flux, 500. What can we do to find the heat rate from the flux? Heat rate, Q, is equal to cross-sectional area times the flux. So you got to multiply the flux, 500, multiply that by 8 times 10 to the negative 4 since it's going into A, so the cross-section of A, that's equal to 0.4. So 0.4 times 1, 33.833 plus 100. It's not right. Sorry, I made a careless error. It does have to be in Kelvin. So let's bring this down here. Sorry, I was rushing a little bit. So it does have to be in Kelvin. Why does it have to be in Kelvin? Well, the temperature that we're going to get is extracted from the resistance times the heat, and we know the resistance is in Kelvin per watt. So it does have to be in Kelvin. My mistake. T2 we know is going to be T2 is going to be 25 degrees C or 298, not 100. I was thinking of the other question. And that's going to be equal to 351.5 Kelvin or 78.53 degrees C. That's the final answer. Hope you all learned lots. Hope you all enjoyed. Let me know if you have any questions. I'd be happy to answer them. Like, follow, comment, subscribe, do all that fun stuff. Hopefully you learned something today, and I'll see you in the next video. See ya.